Okay, so I'm Ricard Alert, and I'm going to tell you about how to use magnetic colloids in order to study phase transitions. So first of all, for those of you who don't know what colloids are, let me tell you that a simple definition is that they are colloidal particles are particles that are large enough in order to be described by classical mechanics, but at the same time they are small enough in order to continuously undergo Brownian motion. Okay, and I had a video prepared here to see what Brownian motion is, but we can skip it or see it when I just finish. And then you may wonder, and why are these colloidal particles important? So basically, they are important or useful because two reasons. There are two reasons why they are important and useful. The first one is because they are very easy to control and manipulate experimentally, okay? For instance, we can just look at them by putting them under a microscope. And this is fairly easy to do, okay? Because they are big enough. And the second reason is that the interaction between any of these two colloidal particles can be tuned very easily. For instance, we can just change the conditions of the solution they are in, or apply an external magnetic field as seen here in the picture, or do whatever, and tune and choose which interaction do we want between any of these two colloidal particles, okay? And so with these super fashioned colloidal particles, what we can study? So basically, colloids are model systems, are excellent model systems for condensed matter, okay? And therefore, we are able to study with them any phenomenon related to condensed matter systems, okay? And the typical examples are the ones that I list here. For example, phase transitions, which is what I study, but also the kinetics of these phase transitions, and also defects present in solids, for instance, or cracking defects or whatever. Also rheology of soft matter, liquids, I mean, lots of things. And also how to assemble complex structures in materials. Lots of things, anything related to condensed matter can be studied using colloids in a very simple fashion. And I just wanted to show you an example of a study of a phase transition in a colloidal system, which is this one. You can see that there's a kind of discontinuous behavior which marks a phase transition here. And I don't want to give any detail other than saying that we can actually see how this phase transition is occurring in real space by just putting the system under the microscope, as you can see in the inset images, okay? You can just see how a phase transition is occurring in real time and real space in your lab, okay? And this is the importance of colloids. And so what's exactly what we study? So in our team, what we study is just, we do theory, simulation, and experiments, everything about a system of paramagnetic colloidal particles that are assembled on top of a substrate, okay? And the substrate is periodic, as you can see in the pictures. There are some stripes, and the substrate is periodic, and then we assemble the colloidal particles on top of it, okay? And since they are paramagnetic, they acquire a magnetization. And with this magnetization, they interact between each other with the dipolar magnetic interaction. And the important point is that the dipolar magnetic interaction is anisotropic, okay? And this means that we're gonna obtain new kinds of phase transitions that wouldn't be present in a system, in a typical system with isotropic interactions, okay? And that's what we focus on trying to know which new phase transitions can we obtain in a system with anisotropic interactions, which we realize via these magnetic colloids. And another thing that we can do is, as I said, we can tune the interactions. And we can do it, since they are paramagnetic, by applying an external magnetic field, as simple as that, okay? And I just want to show one of the results that we have obtained in our lab, which is, okay, let us tune the interaction with an external magnetic field and see what happens. So imagine that without magnetic field, the energetic landscape of the system is the red curve, okay? And I have just put a particle in the minimum of this energetic landscape so that this would be the stable phase of the system, okay? Now let's imagine that I apply an external magnetic field and I tune these interactions, and when this external magnetic field overcomes a certain threshold, the energy just flips down, okay? It gets completely inverted, okay? And it becomes like the blue line here. And so what before was a stable state is now unstable. And the previously unstable states are now stable, okay? We have inverted the stability of all the states of the landscape. And we call this a stability exchange phase transition, because then the system just goes from the stable state, which was before the minimum of the red curve, to the actual minimum, which is the one with the blue curve. Okay? And so we have studied a phase transition in a colloidal system. And thank you very much.